everybody to our second day of the Latin American workshop on observational cosmology. I hope everyone is doing well, or as well as he or she can be in these very stressful times for everybody. But well, the vaccine is coming, so we don't want to, as my father tells me, we don't want to be the last ones to die in a war. So just be careful until the vaccine comes, and we will go out of this. Okay, so the plan is, as I said, I will give each speaker 2 minutes to summarize their talks. Then the posters will introduce themselves, and then I will open up the floor for questions. As usual, raise your virtual hand or write in chat if you want to ask a question. So let's get started. David, the floor is yours.
Great. So my talk was really motivated by a question I was asked about 24 years ago. So when I was working with Chuck Bennett on building WMAP, the microwave background experiment, what Chuck said to me was, we worked so hard to make this beautiful map of the sky. And all theorists want to do is measure a power spectrum. And you take the map and just reduce it down. Now, we're doing the same thing with our large-scale structure measurements. And we're in the process of collecting fabulous measurements. I mean, we've got, looking at sort of where we will be a decade from now. We will have surveyed the sky with the Rubin telescope and with Euclid, and we will have observations from DESI and PFS and the Roman Space Telescope telling us about the distribution of galaxies. We'll have microwave background observations, which through the kinetic and Thermo-Sinier-Soldovich tests will have told us about the distribution of electron densities and electron pressures, and we'll know the integrated mass distributions through the various lensing measurements. And most of what we've been doing is thinking about measuring the power spectrum. Now, for a Gaussian random field, if that's what we have, that's in a sense all the information there is. But even in the measurement of the power spectrum, we usually tend to cut things off on very large scales because of nonlinearities. So what I talked about was kind of a vision of a program of how we can recover initial conditions and forward model the universe using machine learning. And this is something where a number of groups have made progress on this, so much progress in the past year that I am hopeful about this program. There's much work to be done on forward modeling galaxies and also on the inverse problem. Even after you've done the forward modeling, how do you recover initial conditions? And the goal of my talk was to introduce this program, certainly not at a stage yet where we can say this will be a success. But I think this is an area of significant intellectual opportunity. And we will learn a lot about structure formation. I think will motivate us to ask interesting questions about structure formation. So that's what I tried to talk about in my talk. I hope some of you agree. So
thank you very much. Now we will turn to Alex.
Hi, so hopefully you can hear me. While David was talking about the very large scales, my talk sort of focused on the very small scales. So taking our understanding of the power spectrum, which is really great on sort of intermediate scales, and taking it to the extremes where you actually get the formation of the smallest dark matter halos in the late-time universe, and understanding what measurements of those small halos in the modern day, specifically the smallest galaxies, can teach us about what the primordial power spectrum looked like at these very high wave numbers. And the specific reason this is interesting is this is sort of one of the frontiers where the data still do they do some to constrain the allowed model space, but this is one of the places that you can actually push on CDM, and that there are alternatives to CDM that could yield the large scale observations, but could at the same time yield differences in the observed distribution and properties of dark matter halos on small scales. And so I talked about this a little bit more from the observational side with some of the surveys that we're running today to try and detect and characterize the populations of the smallest dark matter halos.
Thank you very much, Alex. Is Farinaldo here? No? Okay. Well, we will go to the poster presenters. Jose Luis.
Hi, Cora. Hi, everyone. I presented a flash talk or one of these posters about a recent paper that they did for detecting and like strategies to detect relative decays of dark matter with intensity mapping. I don't think if I have more time to discuss it right now, but I'm welcome to I welcome you to ask me any question.
Thank you very much. Sunayana Bhargava.
Hello.
Hi.
Yeah, so I think this is the first time I'm speaking, but I am presenting a poster on a paper that I wrote a few months ago, basically looking to try and constrain a particular dark matter candidate, so the sterile neutrino in the 7 keV mass range, because this produces an X-ray photon that is crucially detectable by the current generation of X-ray telescopes. So we discovered that we don't find any evidence of a 3.5 keV line, and we were able to put some of the most robust constraints from cluster studies so far using a novel technique. So I'll be happy to talk to any of you either during the conference or offline, but it's some very exciting work, and I think we should be able to improve on that parameter space even more with future telescopes like CRISM and so on. And I think it's very intriguing because there's other people are working on these different dark matter candidates at the moment that can potentially resolve issues that we have with cold dark matter. The sterile neutrino is also a very interesting candidate to look at, particularly given that it has visible decay products that we can observe with different telescopes.
Thank you very much. Joaquin Sureda.
Hello, everyone. I am a master's student at Chile, and my poster was about primordial black holes as candidates for dark matter. And in summary, it's just to try to derive new extended distributions for these primordial black holes and try to see if some parameters of these mass functions can allow for the total of the dark matter to be formed by these primordial black holes using different observational constraints. And I'll be glad to talk about this to anyone.
Thank you very much. So what we will do now is we will open the floor for questions. Raise your virtual hand if you have any questions for any of the speakers. Rogerio.
I don't know why I have to start, but I start. So I have a question for David and a question for Sunayana. So for David is how many simulations you need to train your neural net, your machine learning algorithm? And for Sunayana is, so you have 117 clusters and you did not stack them to see the signal. And why you did not stack them? So these are the two questions.
Okay, so I would say the answer to your question at this point is we don't know yet. And a lot of it depends on what are we trying to get, what are we trying to fit. For the problem that we've made the most progress on, which is forward modeling the dark matter, and this is work, not my work, but work that Shirley Ho and her collaborators, Yin Li and their collaborators have done, for example. They've used hundreds of simulations. So it's usually done with relatively small boxes. And for the dark matter, you have the Zeldovich approximation working on the largest scales quite accurately. So you just really need to capture the nonlinear scales with the simulations. So their large numbers of relatively small boxes seem sufficient. For understanding, for hydro simulations, this is actually something we're working on right now. And yesterday, Andrina Nicola and I were looking at some work she has done using the camel simulations. This was a set of simulations that we've just done where we've got many small 25 megaparsec cube boxes, looking at a subset of those all with the same cosmology. We're seeing significant variations, what we were interested in measured, which is the electron distribution around galaxies and the pressure distribution around galaxies from box to box, driven by something where we're actually still struggling to come up with the right word for it, which is a combination of cosmic variance and stochasticity, in that one box might have 20 spiral galaxies and 5 ellipticals of a certain mass. Another might have 18 and 12, and that's often driven by very tiny differences. There's a very nice paper that Shai Ganel wrote on what he called the butterfly effect, that you can run a numerical simulation and perturb the last digit in one part of the initial conditions, and one galaxy will end up being a spiral and the other an elliptical. So very tiny changes in initial conditions will lead to these changes, averaged over a very large volume that will cancel. But in my numerical simulation, what's the best way to average over that is not yet clear. Intriguingly, what we saw yesterday, work in progress, is that for fixed parameters, the overall electron temperature within the box turns out to be a pretty good measure of how much energy you've dumped in by feedback. And what seems to be varying, in a sense, the most by the sort of stochastic enhancement of cosmic variance is energy feedback, because some simulations, and actually, of course, some real parts of the universe, happen to contain more energetic AGNs with winds, some regions don't. And those are rare enough events that you can have a fairly big box in your simulation and have significant variation. And this is an example of something where, to me, it's doing this, developing these training sets and looking at many, many realizations of the same model can be very educational. It's a different spirit than a lot of what has been done in computational cosmology. The approach that many of the groups have taken up to now is to run the biggest simulation they can with their best realization of the physics. And I think in my cosmology hat, I'm actually interested not just in the best mean, I'm interested in understanding the variance. And to understand that, you need to run multiple simulations.
Can I follow up on this just 1 second? Because it touched something that I find it very intriguing. If you do have the sensitivity to initial conditions, the Apunov exponents, etc., does that invalidate this approach?
I don't think so, because I think of this approach as ultimately statistical. Like, we can't predict from the initial conditions that there'll be a spiral galaxy at this position. What we can predict, there'll be a dark matter halo. That's causal enough. And then given that, we can predict probabilistically that there'll be a spiral or an elliptical galaxy. I mean, this is usually how we realize things like HOD models, right? Which is just, a simple, but I think somewhat quite incomplete way of going from dark matter halos to galaxies.
Thank you.
So, yeah.
Thank you.
Just to continue that for just 1 second. This actually is interesting for how you want to model the machine learning, because then you're not modeling it as a deterministic process, but as a probabilistic one. And this ties to thinking about how we want to model actually problems like turbulence with machine learning, where again, it is not a deterministic one, but is a probabilistic one. And what you want to capture in reproducibility is matching the statistical properties. And this is quite important if you think about things like quantifying the loss function for your machine learning training, because loss function, for those of you not familiar, You want to compare the difference between what your machine learning does and what you're trying to reproduce. And if you're, I think it's clear in galaxies, but it's even clearer in turbulence. You'd be very happy not to produce the exact picture, but produce all the statistical properties. And that's a different way of thinking from the way that people traditionally think about things in machine learning, where they're trying to reproduce images rather than reproduce the underlying statistical processes. So,
Thank you.
Sunayana?
Hi, Rogerio. So it's a very good question. I think usually when you talk about stacking the spectra of multiple galaxy clusters and like a particular wavelength, the main gain you get is the enhancement in the signal to noise. And that's very important when you're trying to detect lines of some unidentified origin. But what ends up being a collateral of such an effect is that you end up needing to assume some global properties for your sample. So we have 117 clusters. It's a very heterogeneous sample. They have a variety of temperatures. They have a variety of redshifts and so on. So even when we blue shift everything to the rest frame, they still have different ICM properties. So in previous studies, they tend to assume some sort of global properties, or they maybe fit 2 or 3 models in conjunction, and then they sort of average of them. They take an average of them, but you lose information about the individual hydrogen column densities, the attenuation for the individual cluster spectrum. You lose information about the temperature, the abundance, and so on. And another very important aspect of, again, stacking is that you lose information about individual clusters and the rate at which they might contaminate the signal that you might see in your full sample. So one thing that we found is exactly this, that by using a joint fitting, a simultaneous approach, rather than one that just relies simply on stacking and assuming some sort of global properties, is that we can isolate contamination from a subset of clusters that would have ended up masquerading as a signal that you would assume was globally present across the sample. And in the paper, we display that in the 117 clusters in our sample, actually only 3 of them show a statistically significant excess at this 3.5 keV energy range. And the origin of that is obviously very intriguing and still not clear. This could still be an artifact of some data analysis. Plasma codes are not obviously perfect, and we don't replicate the emissivities of various elements in the energy range that we're searching in. So that's something that we need to bear in mind for future studies. But that was our main reason for not pursuing a stacking approach. We could have, in theory, done something where we replicated almost exactly word for word the approach of previous studies with clusters, and then we could have also said, oh, and we do detect a signal at greater than 3 sigma. But we knew that that was a massive caveat of such a technique, which is why we pioneered a different alternative.
Thank you, Sunayana.
Miguel.
Hi. So I also have a question for David. So, so I think there's an agreement that in order, to get, feasible computational times, you need a faster way to do things than full hydrodynamic simulations, right? If you want to do lots of them in the volume you want, in the resolution you want. So machine learning is one possible way forward, but there have been people investigating alternative ways, I guess, right? There's people doing this bias assignment method, and some, I think you can classify them as semi-analytical methods to go from n-body simulation or something like that to a full hydro predictions. And they get interesting results already for the bispectrum, for instance. So my question in the end is, are we sure that machine learning is the way forward? How can we, how do you bet on that? And how is the current status of the bispectrum predictions of these machine learning methods?
Well, I'm not sure it's the way forward. We bet on it fundamentally with our time, right? I mean, this is actually part of a broader question, to sort of take a little detour for the junior people. The most valuable thing we all have as scientists is our time. And we make choices and bet on things by seeing which way we'll pursue them. Why I'm betting right now on machine learning, and I'm doing this actually not just, I'd say, with my own time, but putting my hat on as director of an institute by hiring postdocs and encouraging students to work in this, is that it's a new set of tools broadly. And whenever there's a new set of tools, there's an opportunity for doing something interesting. What I like about trying to go to initial conditions is that I think we actually have a lot of control on the problem to see if we're accurately capturing the nonlinear processes in the bias. I think what we know how to do and is adequate on large scales is just linear bias to go from dark matter to galaxies. If we want to push further, we know we need to capture nonlinearities, capture assembly bias, capture all these things, and there are various methods people have tried. What I worry about when people write down, say, some perturbative approach to do this is we never know if the perturbation series is converged and what goes beyond that. What I like about the machine learning approach is the potential when I recover the initial conditions to show that I'm recovering things that are homogeneous, isotropic, and Gaussian. Those are actually very hard things to get right. So one of the things we've been playing with, actually something I've been working with various students on going back almost 20 years is looking at different ways of capturing things like retrospace distortions and fingers of God. And when Beth Reed did her thesis, we were on the Sloan data, we were looking at ways in which we could undo finger of God effects, and we felt that was the biggest systematic in our modeling of Sloan. And right now, Christina Kreisch is working on this as part of her thesis using machine learning techniques. And the failures are interesting. When you do not do a good job modeling it, you get initial conditions that are anisotropic, right? Because you're recovered in a way in which the radial direction looks different from the direction, other directions on the sky. And we know that we're not in the center of the universe in terms of power spectrum. We know that's wrong. So we can use that to see that we've not done something correctly. And to me, the fact that we've got that control on testing the systematics in our methodology, that makes the machine learning an attractive approach. And it's more challenging for me to see how to do that in other areas. So for example, with HOD predictions, which is now often the state of the art that people use in analyzing galaxy surveys, they match the HOD to the power spectrum and number density of objects and then analyze it. Much of the work with those HODs, if you then go and compute the bispectrum, you get the bispectrum wrong. And when you do that, I don't know what my takeaway should be. If you told me that you've got the bispectrum wrong, but you found evidence for neutrino mass in your analysis of the DESI data, for example, how do I know whether you've seen neutrino mass or this is something not right in your analysis because you're not getting the bispectrum right? You don't have other controls on it. So that's a challenge.
But I guess my worry, I mean, I like, of course, a lot also the machine learning methods. I think they are promising, but the most dangerous thing about machine learning methods is confirmation bias somehow, right? We don't call it confirmation bias in the literature, but that's of machine learning, but that's how it is, right? In the end, you're getting what you're training. And as you said, you're assuming homogeneity and isotropy, which is fine, but at some level, as the precision of experiments increase, that might no longer hold in the real universe, but you might get that from confirmation bias in machine learning. So how do you avoid that?
Well, one of the approaches we're taking to get some handle on this is we're running our hydro simulations with two very different codes. The Simba code developed by Ramil Dave and his collaborators, and the illustrious TNG code developed by Hernquist and Springle and that group. And the plan we're taking is to train on one and analyze the other. And our hope is the difference between different hydro codes run with different parameters is comparable to the difference between the hydro codes in our universe. So that's, I think, one test we want to do. Another important test to do, and I think this is true in, not just in general, you want, by having a broad range of observational data, you can train and test on large-scale structure data and say CMB data, and then make predictions for what the X-ray experiment should see. And if you're missing some of the physics, you're unlikely to get the E-Rosita results right. So I think the fact that, and I see this very much as something where it's not going to be the state of what we will use tomorrow, but I'd like to be in, as we look forward to say 2030, when we've got all these wonderful surveys complete, that we have a set of tools like this that we might be able to use. So that's the thought.
Thanks.
Renan Boschetti.
Okay, thank you. My question is for David. So, okay, my question, I making two assumptions. First, that in principle, you can make an inference of cosmological parameters with this neural networks predictions, because you can generalize the predictions for any cosmology. So you can run MCMC algorithm to infer error bars for cosmological parameters. And second, that this inference is model independent. For instance, you don't need to convert redshift into distance in a box for estimating the power spectrum. Okay, given that these two assumptions are true, if any of these assumptions is wrong, please tell me. But given that they are true, have you tried to infer cosmological parameters with these predictions? And if yes, how the precision in this cosmological parameter inference compares to traditional methods in which you run, for instance, a canned code in MCMC to predict the power spectrum?
Well, I have not done this on observational data, but we've done this on simulations, and several of the groups have done this on observational data, looking at lensing maps. There's a effort that Zoltan Hyman and collaborators in Hungary have done, for example, with lensing maps. And there's some work right now looking at parameters that Francesco Villasquela Navarro here have done. And what they find is you do much better with machine learning than with, say, traditional methods like measuring 2-point functions and 3-point functions. Now, I put a major caveat on that. When you're using machine learning, what you tend to do is you're using all the data in your map. So you're going down to highly nonlinear scales. And what you're doing in large-scale structure analysis usually is you're cutting off at wave numbers of 0.1 H inverse megaparsecs, for example. And there's certainly more information on smaller scales. And if you just ask about, this is one of these precision and accuracy, you can get very small error bars. The question is, should you believe those error bars at this point? And I think that's going to depend somewhat on the machine learning, but to me, mostly actually on the hydrodynamics, making sure that you effectively marginalize over the uncertainties in star formation and the uncertainties in galaxy formation, and how that affects the smaller, the nonlinear scales. And that is very much work in progress. That's something we need to understand. The fact that you see these smaller error bars, and often much smaller, factors 2 or 3 from the same survey, motivates seeing if you can trust these results. So, we have a powerful tool. You need to see if we can trust this tool and where its limitations are. And that's really where I, see this evolving. I would not trust today an analysis where someone said, I applied machine learning to a large-scale structure survey and reached some novel conclusions on the properties of the universe. It is still too early. We need to understand better what's inside the box. But we do have tools for studying that box. So I think that makes it interesting. And my feeling is actually we will probably learn something about initial conditions and parameters, but at a minimum, I think it will force us to think more rigorously about the assumptions we do in modeling in general, because it will force us to kind of go in and look. So I think that it'll be useful that way.
Thank you.
Thank you. Bruno Moraes.
Hi, thanks for the speakers for the nice talks. I'd have questions for both, but if I have time, I'll ask more later, but I'll start with a question for Alex. I was watching your talk and Carlos' talk also. And as a non-dark matter expert, I had this missing satellite problem in my mind. It's a very well-known problem. And it kind of seems that from the observational side, what you're showing is that we're kind of like, we were just missing them and we're going to be able to measure them. And Carlos, from the simulation side, he shows all those like nice multi-resolution stuff. There's some weird, funky things on really smallest scales, which I want to ask him about, but it seems like it's going to, in a certain sense, it seems like it's a bit solved. So I guess if we want to go to precision dark matter cosmology, right? You do touch a bit upon it, but as a non-expert, I guess my question is, if I want to know what we can measure from dark matter properties of different models with stellar stream techniques. I guess that's my question.
Yeah, thanks. So it's good, and I'm interested in, you should ask the same question to Carlos also in an hour. But I think that you're exactly right. I think that if you go back 20 years already, people were saying that missing satellites was not really as much of a problem as it was sort of a communication issue between fields. And I'd say that you hit the main points exactly right. So the things that have come along in the last 20 years are both the observational side, where we're able both to detect much fainter systems, but also understand our selection functions much better. And that's really been promoted by a lot of hard work by, people doing these big surveys of the sky. And then on the other side, from the simulation perspective, missing satellites, as it was originally characterized, was purely a mismatch between dark matter subhalos and observed satellites. And even from the beginning, people were saying we already expect that the mapping between galaxies and subhalos is not one-to-one. And so another thing that's come along a lot is on the simulation side, understanding how you actually form galaxies in dark matter subhalos and what those galaxies look like. And so improvements from both sides have really brought things into better alignment. Getting to your second question about what the major uncertainties are right now, I think one of the main issues is going to be statistics, in that we just have, for these very, very faint systems, for the satellite galaxies, we really only have the local universe to probe. And that's one of the reasons that what Carlos talks about with strong lens systems is really interesting, because it gives you more statistics, more halos to probe here. Another major thing to overcome is really pinning down the galaxy to halo mapping. And so there are a number of different ways to do this. In our analysis, we do abundance matching, but Carlos prefers sort of semi-analytic models. And at the end of the day, you can also do full hydro simulations, and all of these should agree. And right now, it's not completely resolved that they all agree on the smallest scales. And so I think pinning that down, which will come from higher resolution, rigorous simulations, and even better observational data, will help us pin that down. The question about what you can understand from about dark matter properties, right, is really connected to running that entire machinery through, right? So you change something about the fundamental physics of dark matter, that changes your power spectrum. In an ideal world, or maybe using some machine learning approximation, right? you're able to take that change to the power spectrum and run it all the way through to a change in the predicted number of small dark matter halos, and then directly compare that to the observational data. And so if you can get that entire loop running quickly enough and with high enough accuracy, then you can make arbitrary changes to the initial matter power spectrum to test a wide range of different models. And so I think building towards that is really where we're going. And similar to sort of the dark energy multi-probe domain, we really have many different observational tracers that we can use, and they should all give consistent answers at the end. The dwarf galaxies eventually, fall off in power once you get below the threshold of galaxy formation, but strong lensing and stellar streams, some really interesting novel probes using astrometry to detect subhalos, all of these should be giving the same answer for the abundance of small scale structure.
Thank you. Dante?
Okay, thank you. Can you hear me?
Yes.
Okay, so I have two questions. One for Joaquin, the other David. I will ask first to Joaquin. Sorry, are you hear me okay, or is difficult? I have a very bad connection.
I just didn't hear the name of the person you're asking the question to.
Sorry, one for Joaquin and the other for David. And for Joaquin, to Joaquin, I have seen your talk and your poster is very nice. And I have you have showed two scenarios for primordial backfall formation, and in your last plot you are showing some regions of the mass function, and my question is, have you checked how easy it is for our current understanding of the cohomological model? I mean, using, I don't know, the background parameters of our model today. Have you checked how easy it is for those scenarios to form primordial function with those parameters in those regions? If my is clear enough, could you tell me if you are understanding?
Yeah, I think I understood your question, but the thing is that as for now, we are just using and just moving from different parameters for these mass functions. So the thing is that we're just assuming a standard cosmology with the standard cosmological parameters. So we are not actually like constrained, for example, cosmographic parameters, for example, omega matter and omega radiation, for example. So the thing is that the only thing that we're assuming is that...
I'm wondering... Sorry for interrupt you. I was wondering if there is some model for the evolution of primordial black holes in a way that you can check if those parameters are the evolution of black holes in a background cosmology, just like we have today, or something like that. I'm not sure if there is something in the literature, or if you are planning to check something like that.
In the literature, the most approximate thing that people have done is to consider that since these black holes can evaporate, for example, and they are formed very early in the universe, they can affect, for example, the content of radiation in the universe. So there are some papers, some people that they actually study the evolution of the cosmological parameters, considering this primordial black holes contribution. So you're transforming matter content into radiation content, for example. And there are works actually, for example, constraining the H0 parameter, for example, using this approach. There's a little number of works on that.
Thank you.
Okay. Thank you. And my last question is
actually,
David.
Because Bruno also had two questions, so you will go down to the line for the second question.
Okay, no problem.
In case we run out
No
of time,
problem. Thank you.
I want to give everyone the opportunity. Okay, Martin.
So, hi everyone, I am Martín de los Ríos. I am a postdoc at ICTP-SAIFR in San Pablo, so I was really looking forward to have you all here in San Pablo, but well, I hope for next year we can do it in person. So I have a question for David. I was wondering about the output of this machine learning simulation, if you can expand a bit more in the output, because as far as I understand, the output of the simulation in this moment is the dark matter particle position at redshift 0, so one snapshot. So I was wondering about the size of the box of these simulations, the number of particles, also if you have access to the velocities of these particles, or if you can expand the output to have more snapshots and build merger trees and these kind of things.
So there are, many applications. Well, yes, first, I think we all wish we were traveling. We all wish we were able to go out for a nice dinner tonight, that we would be gathering for drinks and talking more about this over drinks. But this is the year in which we live. 21 will hopefully be better. So anyway, there are different groups who have applied this to different sets of problems. So one of the things, for example, one of the things that we've done is make predictions for microwave background temperature and thermal Sinyes-Soldovich and kinematic Sinyes-Soldovich maps. There, what we've done is use machine learning to go from dark matter. Actually, first we use analytical models to go from dark matter to what the gas does. Here, this particular case, we're using the Battaglia model. Then we train the neural net. This is work that Leander Thiel, a graduate student at Princeton, has led, to go from the predictions of the analytical model to match the numerical simulation. And that we train on, that particular case, on the illustrious TNG simulations. Having done that, we can then turn to a big n-body simulation. And right now it's possible to run quite large n-body only simulations and use the neural net to go forward and produce lots and lots of simulated thermal Sinyes-Soldovich maps. So we can do lots of them quickly with only the need to run an n-body simulation. So that's one program. Another program, and this is work that I'm not part of, but have been following closely by Shirley Ho and their collaborators, where what they do is start from initial conditions, use the Soldovich approximation, and then train the neural net to go from the Soldovich approximation to reproduce the large-scale structure on scales of megaparsecs and bigger. There, they've been primarily comparing displacements as opposed to velocities, which are, of course, the derivative of the displacement field. But there's nothing that would stop them from trying to predict velocity as well.
Perfect, thank you.
Mustafa.
Yes, my question is, I missed part of this discussion, so my question is for David. So maybe he already mentioned this, but anyway, I will ask the question. So my question is there a way, or is there in this procedure to go to recover the initial condition or probe the initial condition? In this approach, is there, for example, a wall? Is there a wall? Why I'm asking this question? Because, for example, can this method approach be pushed even earlier? So recovering the initial condition, whether there is Gaussianity, homogeneity, isotropy, but is there a way to put it, for example, for pre-inflation, to see the initial conditions before theories of the early universe? I would be interested to hear what the comments about that.
Well, I would begin with a caution. Well, first, good to see you.
Likewise.
Machine learning is only as good as your training set, right? So you train on data, you train on models, and you can get the neural net to replicate what is seen in the trained data. So someplace where I think we have some confidence is our ability, for example, to model dark matter only simulations. I think we're now at the stage where we capture that physics correctly in dark matter only simulations. So if I can train a neural net to do that, then that's sufficient and I can test that. What you want to do is to go back to pre-inflationary conditions, and then you'd have to ask, well, how would I train it? And what would I train it on? Now, if I had a particular model of reheating that I wanted to reproduce, I would, be able to perhaps use machine learning to be able to do that more quickly. But I think at this point in thinking about particularly the pre-inflationary universe, we are limited not by our ability to do calculations, but by our ability to understand the physics. We need better physical principles. So, one of the things I was asked about was, did I see machine learning helping to solve, the problems of, say, string theory? And I don't think so, because those are not problems where we need to simulate more quickly, but problems where we need to have improved physical understanding. I don't think the neural net will, it doesn't learn more than what we know already in a sense. We have to have a way of training it. And in fact, we have to be, this is a general challenge for neural net, for machine learning. You have to be very careful about what you train it on, right? There's a whole area which we mostly don't have to worry about in our simulations for our field about intrinsic biases. When people, apply machine learning to giving out mortgages, you don't want the neural net to propagate the biases you already have. I've been told an example just to show you how this propagates. It can be, some company decided to train the neural net on how it processed job applications to see who they'd make offers to. And what the neural net learned to do was throw out all applications by women, because they were doing that at some lower level in their data. And the neural net just learned to do that more efficiently. So, the neural net can take the limitations of your data, the limitations of your method, and make it worse. So you have to be, there is caution that must be applied with these things.
Okay. Thanks.
Thank you. So we now have, this will be the order, Bruno, Dante, and then Mehdi.
Thanks. Okay, I'd like to also ask another question to David. So it is very related to what you just said about training. So there's what we're doing has a certain measure of transfer learning, right? So you said something in your talk that surprised me a little bit. So you said that you were able to train with very few cosmological parameters and then apply your nets to other simulations with other cosmological parameters. And I'm familiar with the concept of nets are good at interpolating. So if you try to populate your your space of parameters. You can use inside. If you extrapolate, it's a bit more dangerous. There's some work by Alexandre Fergier's group, and I'm a bit familiar with that. I'm comfortable with stuff where you can cover your perimeter space. So if you're doing, let's say you want to, it's a matter of mappings, right? I'm sorry, the question is a bit complicated, so I'm trying to refine it as I ask it. So it's a matter of mapping, right? So if you're using, if you have an analytical model and you have simulations that are very complex and you have the same cosmology for both. When you're training, what you're doing is that you're learning implicitly a very complicated nonlinear map between your analytical predictions and what you're seeing on the simulations. Conversely, if you're trying to measure a train on different cosmological parameters and then find cosmologies that you haven't put in, you're building a map kind of orthogonal, let's say, where you are learning to map between cosmologies, right? Now, what you seem to be saying is that you could use the analytical to train more complicated simulations from a given set of parameters, which to me is a map in that direction. And that this would also work, this direction would work if you translated it to another cosmology. So it seems that transfer learning was working well. But what this seems to me to be saying qualitatively, implicitly, is that your small scale physics is not as dependent of cosmology, because otherwise I have a hard time understanding how you could do that transfer, and the transfer would guess your cosmology correctly. But if you're mapping from the analytical to the more complex nonlinear stuff, it's very, very little sensitive to cosmology. Then you can transfer that map, and it won't be affected by the cosmological parameters, right? You don't have that issue. So I'm not sure I understood it correctly, if that's what's implicit in the argument. I was wondering if you could give us a more like qualitative view of what you meant by that, and if I'm interpreting correctly. Thanks.
Okay, I'm going to try, we'll see if this works, to draw a picture. You'll at least see how I wave my hands. So the issue is exactly as you stated it, right? So what example, and this is mostly work that Shirley Ho and her collaborators have done. So I'm really describing their work as opposed to mine, but where they've trained the network to say with data with omega matter of 0.3, and they run it with omega matter of 1. But what they've done is they've used an analytical theory. So the analytical theory has, well, you're completely correct in that interpolation is safe, extrapolation is dangerous. So what you've done with the analytical theory is remap the problem you have back into the region in which you are able to do interpolation, is my understanding. And I think of this as what, if I apply Zeldovich to describe particle positions, what Zeldovich tends to do is overshoot in clusters, right? And if you look at something that's run with only Zeldovich, the clusters are too fuzzy. And if I had to go in by hand using this neural net, I would say, I know if I've got a region like this, I want to redistribute the particles so that everything looks like an NFW halo. That's what my neural net would say to do in my head. And I believe, but we haven't rigorously shown, that's what the network is learning. And this, you would do this mapping from the particles forming a region like this that's kind of fuzzy to an NFW halo. Whether omega matter was 1 or 0.1, where I trained, I need to learn this mapping, and that's a property of the way nonlinear evolution happens. And I believe that's what the network's learning.
Okay, so I guess my intuition was a bit correct, but essentially I'm restating what you just said. In a certain sense, what you're saying is that when you get to the very, very nonlinear scales where the Zeldovich approximation breaks down, your gravity doesn't sense the cosmological densities too much. In a certain sense, it would be saying how much cosmological information you have on your very, very local peculiar velocities, and the answer is not much. So the next question would be, if this is like a 3% effect, and you try to do a measurement that uses this, how much would you be getting it wrong? But I guess we're not at that stage yet.
We're not at that stage yet. And of course, I think you'd always want to, if you're finding that the parameters you're getting are outside your training zone, even if you've seen extrapolation work reasonably well, you'd always like to check with something close. I guess otherwise you wouldn't trust it. It's also, I mean, it's actually just in terms of understanding some of the physics, it's actually interesting to say, okay, so NFW we know is a reasonable approximation. What if we really want to get the outer profiles of a halo right? There's been a bunch of work, papers by Deemer and collaborators, for example, showing that late accretion, that the outer profile is sensitive to the late accretion history. And that tends to be sensitive to the values of omega matter. So if I really care about getting that detail right, I probably have to get that omega matter right. I've also wondered, and this is actually an interesting thing just to look at in the simulations alone, you know, if we're interested in galaxy formation, and this is if I know the dark matter density at redshift 0, but only the density at redshift 0, is that enough to predict where the galaxies are? Or do I need to know the whole assembly history to predict where galaxies are? Is there information encoded in the outer regions?
Okay. Okay, thanks. Thanks a lot.
So I see someone say, Carlos Frank convinced them not to trust NFW. Now,
No, I was just kidding. It was showing it was so good, it's unbelievably good in the sense that it's becoming unreasonably good. It goes all the way to small scales, to the Earth scales, and
anyway. Yeah. No, I don't know.
It's no longer reasonable.
Yeah, no, but it is. I think something we don't, fully understand is what is the, it's a pretty large range of parameters over which you get something that looks like NFW. I think if I go back to models we don't think about much anymore, things like hot dark matter models, where you have very different physics, then finally things don't look like NFW. Or to go to dwarf galaxies where I can start thinking about self-interacting matter, dark matter, or warm dark matter, or fuzzy dark matter, you can get things not to look like it. So, the exceptions to this are very interesting.
But you have to go to the extremes because NFW works over the domain, the large scale domain, right? So yeah, it's on the boundaries, the peripheries where we're pushing.
Okay, well, sorry, David, I interrupted you.
Sorry, I have a 10 o'clock meeting. I was
actually about to close this. Thank you very much to the speakers and to the participants for a great session today. Nice seeing you all. See you in 2 hours.
Thanks, guys. Bye-bye.
Bye-bye.
Next year together.
Thank you.
Yes.